Assalamu alaikum guys. So this is Najmisha Shah. Today I came to explain you about what the new chapter under Unit 1 Atomic Structure, the electronic energy levels of atoms. So let's move on to the contents. Actually, this is what until now we studied about what the atomic structure, the theory of the matter, atomic matter, and from that we have studied the several things: iron, atom, and the scientists' innovations, Planck quantums, photons, and how. What about the subatomic things and everything we already completed. So now we are going to step into the new thing here. Here we are going to speak about what the electronic energy levels of atom. For that sake, first we have to know about the ionization energy. So the definition and the understand it's really needed. The next thing is the hydrogen spectrum. Under hydrogen spectrum, we are going to speak about the two type of the spectrum. That is, one is the line spectrum, another one is the continuous spectrum. Then we are going to speak about electron emissions in hydrogen. Finally, we just going to compare the line spectrum of hydrogen according to what the frequency and wave. Let's move on to the introduction. According to that, chapter is belongs to what? The electronic energy levels of atoms and the atomic structure. Right. So first we have to know what is meant by ionization energy. Yes. So the ionization energy means what? Ionization energy of an atom or ion is the minimum energy. The word is very important, guys. What they are telling is we are speaking what the minimum energy which is required to remove an electron, right? An electron from the ground state of isolated gas or ion. This is what we are talking about. So simply you can say what is meant by the ionization energy of an atom or ion, right? When we speak atom, that is neutral one, there is no charges. Ion means what? It is able to carry positive or negative, right? Is the minimum energy is required to remove an electron from what? The ground state of the isolated gases and an ion, or you can say the minimum energy what you need to remove the electron from the loosely bounded electron from the valency shell electron. This is what you have to know. What is the definition? Again, I will say, what is that minimum energy? Remove to what is that minimum energy? It's required to remove an electron from your valency shell where the electrons are loosely bounded. Such energy is called as what? Ionization energy. Hopefully you should understand, right? So the magnitude of the ionization energy tells how much of the energy is required to remove an electron, right? I say when we are speaking about the ionization energy, we are speaking that is a kind of energy. You need to remove an electron on your valency electron. So just imagine yourself like that. This is what your atom, right? Having the cells. So valency electron means this is your valency electron. You need an energy to remove. Right. So for that energy is called what? Ionization energy. This is what the simple explanation. So what they are telling here is the magnitude of the ionization energy tells us how much of the energy required to remove an electron, right? So this is very important, guys. Greater the ionization. Okay. This is very important. Greater the ionization energy, more difficult to remove the electron. Why they are telling is, guys, when you have, just imagine yourself, If it is the stable one, right, I just mentioned the atom as a 8. So if it is strongly bounded, you have to provide what? More energy. This is what they are telling you. The greater the ionization energy, it's more difficult to remove the electron. The word is clearly mentioned like that. So you should be very careful about that. How much of the energy needed to remove an electron from your valency shell, right? So according to this, we'll go for the next. So the ionization energy for a given element increase as successive electrons are removed. I said when we speak about the valency electron, so the ionization given element is increasing. How? If the successive electron removed easily, then the energy also increasing. So according to that, this trend is because with each successive removal, an electron is being pulled from an increasingly more positive ion and require increasingly more energy. So if you read this content, right, you might confuse. What they are telling is simply you can understand, right? So look at here, when you use the successive removal means what? We have to pull the electron from what? Your valency electron shell, right? Electronic shell. So what if you lose one electron means what? It will form the positive ion, right? This is the concept. So once if you pulling the one electron means the positive ion, yes, also increasing, therefore the energy you need to provide that is also will be increased. This is what is telling about this statement, right? So according to that, the sharp increase in ionization energy that occurs when an inner shell electron is removed is a clear evidence for the fact that electrons are discrete energy. So this is what they are telling is you can see a sharp ionization energy. How? Let's see. Right. When you take the stable configuration, okay, any atom, right? So it will end up with what? NS2, right? You have something, right? And according to that, NS2, okay, you are not. Okay, we'll speak about that. Your who is that neon? So what is the electronic configuration of the neon, right? Still you are not familiar with NS2, so we will go forward the 2. So when I speak about the neon, what is the atomic number of the neon is the 10, 2, 8, right? So if you say it's like that, this is what we are telling is the stable configuration, the 2 and 8. So therefore, you have to provide more energy. Why? This is very stable configuration, right? So you have to provide the more energy to remove the electron from this configuration. So that's why when you see, you can see very sharp increase of the ionization energy once you get into the stable configuration. Why? You know the stable configuration means what? The nucleus and the electron attraction is more high. Therefore, you have to provide the more energy. This is what we are telling is the stable configuration having what? The highest ionization energy. Right. Let's say clear also. So according to this, right, now we are going to see the successive value of ionization energy I for the elements from sodium to argon. So you will study the trend of the ionization energy and everything is the end of this session. Now I'm just talking about what the electronic energy levels of the atom according to the ionization energy. So I'm just taking only what the second periodic quadrant. Okay. So sorry, your third periodic. Therefore, so look at here. This is what the sodium to argon, your third periodic table, right? So the sodium is, you know what is the electronic configuration, right? So according to that, the end of the sodium is I1 is little less, right? It's 11, so you will end up with what? Okay, if it is 11, you will end up with 2, 8, 1. So by looking this, you should be very careful what? The removing one is not that much hard. So you have the less amount of the ionization energy. But now we have to be step into the highest ionization energy. Why? It's a stable configuration. The 2-8 means. To remove an electron from the stable configuration, why the attraction between that valency electron and the nucleus will be very high. Therefore, you have to provide the more energy. Therefore, your second ionization energy is very high compared to the first ionization energy. Why I1 is less than, always higher than, less than the I2 for sodium. This is the reason. This is what is the reason why I1 is always less than the I2. When you reach to the stable configuration, then you have to provide the more energy to remove one electron from the stable configuration. That is the reason. And look at your magnesium now. It seems to be similar. Why? What is the stable configuration of the magnesium is 282. So when you take the 282, right? From this, your first one is removing one electron is easy. And the second electron also easy. One is step into the third electron. That means what? Again, it came to what? The stable configuration. Again, this is stable. So when you step in the stable configuration, you can see what is happening. You have to provide more energy. Why? For that sake, it's magnesium high. Likewise, look at here. After that, your argon is a stable one. Always is I1 is high for the argon. I2 also highest for the argon. When you compare for all elements with what? Each ionization energy, the argon will get highest one. Why? Always it will stay at the stable configuration. Yes, I can use this word. Right, your stable configuration. This is the reason why we are speaking about the successive values of the ionization energy. Right. So, yeah. Next, we will step into what? The hydrogen spectrum. The spectrum is very important under what the atomic structure. So here we are going to define about what is mean by spectrum. The spectrum is produced when a radiation from such sources is separated into its component wavelengths. So this is what we are calling is a spectrum. So you should be very careful about that. What is that spectrum means? When the radiation from a source, right? However, you will get the radiation from a source. It's separated it into component according to what the wavelength. This is what we are talking the spectrum. The spectrum having I already discussed with you all, right? We have two types of the spectrum. One is the continuous spectrum, another one is the line spectrum. First, we will go through the continuous spectrum. What is meant by the continuous spectrum? This range of colors containing light of all wavelengths. You should be very careful about that. That word call. The word call all wavelengths. Right? The range of the color containing light of all wavelengths, which is called as what? The continuous spectrum. Right? Even though. Not all radiation source produce the continuous spectrum, right? When a high voltage is applied to a tubes that contain the different gases under reduced pressure, right? The gases emit the different color of light. So according to this, what we already said is the range of the color containing light at all wavelength. We said that is what the continuous spectrum, but it's not true for the all time. The radiation produces a continuous spectrum when you all use the high voltages applied to the tubes containing the different gases under the reduced pressure, the gas emit from the colors of light. This is the basic and the major example what the neon gas, which is able to emit what the red orange glow. When you connect like this under pressure, reduced pressure, this glow of many is called as what the neon light. So this is what actually this is called what the neon lights, because of what the radiation source produce the continuous spectrum. So under when you use these circumstances, right, only the neon light able to produce what the red glow, red orange glow of light. This is we are called what the neon light. Step next, when light, this is what I said, the continuous spectrum. But when a light emits from such tubes to pass through a prism, the word is very important, guys. I will use another color to explain this. When it pass through the prism, right? Only the few wavelengths, I already said you can see what is that at all wavelengths producing the color is a continuous spectrum. But when you use the prism, right, a prism, only the few wavelengths present, the resultant spectrum, such containing radiation only at the specific wavelength. This is very important, guys. You should be very careful about that. Only at the specific wavelength you can see the resultant emission, right? The resultant emission. This is what we are calling is line spectrum. So this is a major example for what. Let's we move on to the line spectrum of the hydrogen. It's given in the next slide, right? So let's say keep an eye of the hydrogen. So what is happening? You ask, this is what I talk about the continuous spectrum of the hydrogen, sorry, line spectrum of the hydrogen. So already we said when the radiation emit all wavelength, you can see the lights are of the color, that is called what the continuous spectrum. But the line spectrum, it will produce the color of the radiation, that light only at the particular wavelength, right? Only at the particular wavelength, that is what we call that is line spectrum. So scientists studied the line spectrum of hydrogen thoroughly in mid 1800s. So you can see that is where should be very careful and clear about that. And look at here, you can see the line spectrum of the hydrogen, right? Only in the 4 lines, you can see 1, 2, 3, 4 lines there. The wavelength at the particular wavelength, they clearly mention, you can see that is at only the particular wavelength. The first one is the wavelength of the 410 nanometer. This is what they are saying. 410 nanometer, that is violet in color. Right? And next one is what? 434 nanometer. Yes. Let's we move on to this. Yes. What is the color of this? Blue color. And next one. 486 nanometer. The color is blue green, right? So you can use this. This is what. And later, which is what red in color, the 656 nanometer. So we are telling this is the red color. So you should be very careful about that. The line spectrum means it emits the source of the radiation only at the particular wavelength, and you can see the radiation line only at that particular wavelength. So this is what we are calling the line spectrum. So you can see under the hydrogen line spectrum there is only four color. The four color means what? The four color means what? You can see at the 410 nanometer that is violet in color, 434 nanometer that is blue in color, and 486 nanometers blue green color. Finally, 656 white that is red in color. So this is what we have talked about the line spectrum. Then the Bohr atomic model, together with the Planck's idea that energies are quantized, was capable of explaining the spectrum of the hydrogen. Right. So then we had an idea of what this is the diagram. It shows the possible electron emission in hydrogen, which derived from what the Bohr model extended with what the Planck idea. Right. Look at this. This is what we are telling is the possible electron emission in the hydrogen spectrum, right? So still we are speaking about the line spectrum, and this is what I will tell you the different series presence, right? According to this, can you define what is mean by this 1, 2, 3, 4 is the quantum number, the different, yes, the differential, right, for particular one. That is what the quantum number. So n1 means this is n1, 1, 2, 3, 4, like that, right? It's increasing. So you can see it's very clearly. I will use the spotlight, right? So we are going to speak about what? The energy kilojoule per mole. So according to this diagram, you can see the energy is increasing. And what is this? The distance between the N1 and N2 is 1 is 2/6. But when you go for the N2 and N4, N3, that is what you should be very careful about that. It should be 3/4, right? So can you define what is the space between the 1 and 2? The same is what the 2 and 8, right? So by the way, it has reduced by 1. Why? This is what the half of this 4. When you take 8, the 4 is what? The line of 4 is half of 8, right? When you speak about the third energy shell, that should be what? In between the distance between the 2, 4, half of 3. Sorry, half of that. So that will become as a 3. Likewise, when you select the 6 and 8, 4 and 8, again you have to select the half. From that, the third corner will come 5, 6. Likewise, the energy levels is increasing. Finally, the gap between these energy level will overlap and it will become as a 5. So this is how the energy level is overlapping. So when it's become reached to the infinity, right, then as the energy is increasing. So the possible electron emission in the hydrogen. So usually whenever we speak about the possible electron emission in the hydrogen spectrum, there are 5 series. The first one is we are talking about the Lyman series. And second is a Balmer series. Third is a Paschen series. Fourth is a Brackett series. And final one is the Dupont series. Right. These series you should know there is an interconnection, right? You should be very careful about that. So let's be clear this term, right? Okay. When you take this Lyman series, right? So according to the Lyman series, what they are telling is, you can see the Lyman series, okay? Okay, Lyman series. When you take the Lyman series, you can see the n is always 1. So this is what you can see. The electron is falling from what? The N2 to N1. Should be very careful about that. Therefore, always when we speak about the falling in a energy of the electron should be what? N final. You can say N final minus N initial. When you say about this N final to N initial, it's always what? What is your N final is 2. No, sorry, N final is 2. So that means your Lyman series is 2 minus 1. So this is what the N initial is always 1. That is, this belongs to what the Lyman series. So I was speaking about what the energy shell, that level of the shell, but under this, when you speaks about the energy, right? So energy at what we are telling is E, energy of final, right? Minus the energy of what? Initial. So when you speak about that, take this Lyman series, the energy of the final is, okay, 2 minus 1. So 3 minus 300 minus 328. So you have to make, right? So we'll make a bracket. That should be clear for you all. Right. And next, minus your initial one, that is what? Again a bracket. Minus 1, 3, 1, 2. This is what we are doing. So this is how we are finding the energy between these transition, the possible emission of the electron. So this is belongs to the Lyman series. What I'm telling is, guys, you should be very careful about that. We'll use another color. So always the Lyman series is, the N final is always 1. You can see this is coming from 2 to 1, and again 3 to 1, 4 to 1, 5 to 1, 6 to 1, 8 to 1, and continuum to 1. This is what called Lyman series. As like this, step into the Balmer series. The Balmer series N final is always 2. So this is what we are telling. You can see it's coming from 3 to 2, not 1 to 2. You should be very careful. So falling, possible electron emission falling, right? So 4 to 2, 5 to 2, 6 to 2, 8 to 2, continuum to 2. And again, we are taking the Persian series. Yeah, Persian series, what? Again, your NF. What is your NF? Yes? Guys, yes, you should be able to tell now. That is, now it's free. Okay, likewise go for the bracket, right? Bracket, what he said, what is your NF, your final electronic shell? What is the number? That is what 4. And your final one is the P fun. The fun issues what? The NF always 5. Should be clear about that, right? And the following and the series and everything should be clear. Right. Now we already discussed all steps. And let's see the notes. Yes, they each allow the orbit around the atom. I said, right, that electron shell, that is your orbit corresponding to the different values of n. The n always the whole number. It's a positive integer, right? The radius of the orbit gets larger when the n increases. I already said the number of the orbits will get the larger if the number of shell increases. So that's the first law of the orbit. The one closest to the nucleus, yeah, has n1 is 1. And the next allowed to the orbit, the second closest to the nucleus, 2 to 1. So this is what we are telling is which is closest to their your orbit. That is what we are finding the energy level. So according to that, the line spectra are result of emission when electron fall from initial energy level Ni to final energy level Nf. So you can say E photon is equals to, right? You can say the E photon delta E is equals to E final minus E initial. It's always they are telling you will end up with minus value, right? So therefore, this is for all transition. So delta is the negative for the emission. As NF is less than the Ni, I said right, the electron is falling in energy to a lower energy orbit. So the possible emission result, the line spectra seen in hydrogen. This is how the line spectrum is derived. So you can see here, this is the variation what the hydrogen, the line spectrum of the hydrogen, it varies according to the frequency. You can see this is the, yes. You can see this area, this is what increasing side of the frequency. So you know the relationship between the frequency. Yeah, C is equals to lambda mu, right? According to this, right, guys? Yes. According to this, when you take the C is equals to lambda, this is constant. As your lambda increases, now your wavelength, sorry, frequency should be decreases. According to this, you can have an idea about that. Always the Lyman series will become first, but this increment according to the frequency, therefore your Lyman series have highest frequency and the lowest wavelength. The other connection I will show in the next slide. So this is very important, guys. When we speak about the Paschen series, it always belongs to the IR radiation. And the Balmer series, he is the person which is able to show the color radiation. So he is a partly visible series. The Lyman series is UV ultraviolet series. So you have to know this connection and everything, right? So let's move on to, let's move on to the next slide and you will understand what we are talking about. So this shows what the line spectrum of hydrogen, the variation of according to wavelength. I said right, so always the Lyman series is lies first. Okay, I already told you, right? The Lyman series always lies first. Why? The wavelength should be less than. That shows the lowest wavelength, and also it will show what the highest frequency. When you say, right, the Lyman series always NF is what? 1. The N initial, the final always 1, which is closest to the orbit, which is closest to your nucleus, right? But the N initial, the falling from the what? The electron falling from the other orbits, right? It should be either 2, 3, like that. And when you take the Balmer series, right, you can see NF always what the stable one. The N initial, the initial energy level will be very 4, 3, like that. Even though 6 or whatever. And this is belongs to what the Paschen series. This is what we are studying. And according to this, it's increasing the wavelength from left to right. The Lyman series to Paschen series, therefore, this one will have the highest wavelength and it will show the lowest frequency. Right. So this is what, guys, I have completed what the electronic energy levels of the atom, right, and the atomic structure. Hopefully, guys, you all understood this chapter. Inshallah, we will meet on the next new chapter. Until that, see you. Bye bye, guys. Assalamu alaikum wa rahmatullahi wa barakatuh.